welcome you all. I'm Meghamala, and today's topic is about the problem solving in sequential logic. So today we will see how a few problems based on the sequential logic. So we all know that sequential logic in the sequential logic module. This is the fifth module where we have discussed in the earlier classes. So sequential logic talks about the different sequential machines. Okay, different machines. So far we have come across the machines which are based on the states, okay, state diagram, state equation and state reduction problems as well, how to solve. So now we will see a few problems based on this sequential logic. So before that we will see that sequential logic consists of two basic machines. Okay, so the two basic machines are Moore and Mealy and Moore machines. So we all know that what is this Mealy and Moore. So before going that Mealy and Moore, the sequential logic deals with the synthesis and analysis of synchronous and as well as the asynchronous sequential circuits. Okay, synchronous and as well as the asynchronous sequential circuits. Synchronous sequential circuits are nothing but they goes as per with respect to time. Whereas asynchronous sequential circuits are nothing but they go, they just don't consider the time constraint. Okay, and now coming to the Mealy and Moore machines, we see that in the Mealy machine, the output depends upon the present state and the present input. So these are the two important machines to be considered, and here by considering these two machines, we can switch on from one machine to another machine as well. Okay, by various algorithms can be considered in order to switch on from one machine to the another machine. So coming to the Mealy machine, we are saying that the output, okay, the output depends on upon the present state and as well as the present input. And in the Moore machines, the output depends only on the present state. It doesn't depend about the present input, but it just depends upon the present state. And generally, it has fewer states than Moore machine. So Mealy machine has a few more states other than the Mealy machines, and in the Moore machines we see that it has more states than Mealy machine. So Moore machine will have the more states, whereas Mealy machine will have the less states. And then the value of output function is a function of the transition of the charges, and the input logic of the present state is done. So here, based on the output, how the output can be observed is with respect to the transitions and the changes. Okay, functions of the transitions and the changes when the input logic on the present state is done. So when the present state, see here we have in the Mealy and Moore machines, we have the different states represented as S1, S2 and S3, so on, right? So these are the different states that we can consider. If you are considering these states, I can say that S1 will be my present state and S2 will be my next state, right? So here what we are saying is, when the input logic on the present state is done, when the input logic, see here, once you're done with this input logic, when you're applying some logic onto this present state, then only you can able to get the output for the next step. Okay, and then the value of output function is function of the current state and the changes at the clock edges. So here the output, the present state and the next state of the output always depends upon the present state of the input. And then Mealy machines reacts faster to inputs, whereas the Moore machines it decodes. Okay, more logic is required for Moore machines. We require more logic, whereas the Mealy machines are simple to construct and also they are faster. Okay, and then they generally reacts to the same clock pulses, whereas for Moore machines they require more circuit delays we see, and then they generally react one clock cycle later. So here we see that the Mealy machines, they react, or as the clock with respect to one clock pulse we can able to get the output, whereas for Moore machines it reacts to more number of clocks. Whereas if you compare both Mealy and Moore, Mealy is a better one to consider. And now we will see the sequential machines. So the sequential machines is finite automata may have outputs corresponding to each transition. So here we know that the previous slide is all about adjust or else a difference between both two machines, Mealy and Moore. And now we say that these are nothing but the finite state machines. Okay, finite state machines, Mealy and Moore. So in the Mealy is FSM. That's a finite state machines whose output depends on present state as well as the present input. Okay, it depends on present state and as well as the present input. And here it can be described by 6 tuple. So where see here we have 6 coefficients with respect to the finite set of states with respect to the states, symbols, okay, symbols of input, symbols of output, and also with respect to the transition, input transition and output transition, and then the initial state. Okay, input transition, output transition, initial state, and the states, number of states, and as well as the alphabets, or else alphabets pertaining to that particular symbols. And then we will see that state table. Okay, each machine will have the states and as well as the state table, followed with the state diagram and then state equation. So this is a scenario that we can see in the finite state machine. So coming to the state table, we see that we have a present state and as well as a next state. So present state consists of all the present states that you have. So if your states are of 4, then give the name as A, B, C, D. And the next state has based on the inputs. Okay, if the input is 0 and if input is 1. Okay, if my input is 0, the present state, the output goes as x1, and when my input is 1, my output goes as x1. Okay, likewise, when my present state is b, my output goes as x2, and when my input is 1, then my present state goes as x3. So see, I said you that each and every finite state machine have state. Okay, state diagram, and state diagram we can obtain it from the state table, and the state table can be obtained from the state that you are considering, and from the state table we can write state equation. So this is a scenario that we can see in the finite state machine. So this is a state diagram, and this state diagram I have obtained from the state table. So these are my 4 states, A, B, C, D, A, B, C and D. And here we can see that these are the direction lines. So each and every state diagram consists of states represented in the circle and the direction lines. Okay, and the direction lines, and also input and output. Input, output, direction lines representing, and the states. States we are representing in the circle. Okay, so states representing the circle, direction lines, and input and as well as the output. So we have A, B, C, D, and from the A, if my transition is taking place to state B, okay, from state B, my input is 0. When my input is 0, what happens is, I can say that my output is x1. Okay, and now when my present state A, if it is taking its transitions to C, okay, then if it is taking my transition to C, how can it go? It should go from A to D and D to C, right? So if it is from A to D, then what? At input 1, with respect to A, at input 1, my output goes as x1. Okay, likewise, if you this will be my present state, and this would be my next state. And in the second scene, I can consider my B as a present state and the rest as the next state. Okay, so this is how I can draw the state diagram based on the state table. And then we see the Moore machines. So just now we have compared, right, Mealy and Moore. When you compare the Mealy and Moore, we see that Mealy is faster and it requires less number of clock circles, right? Whereas Moore is a bit slow and it requires more number of clock signals, right? And then we will see the Moore machines. Moore machines is a FSM, that is a finite state machine, where the output depends only on the present state. Okay, the output depends only on the present state. So here also it has 6 tuples, where each and every coefficient represents the state. Q represents the state, sigma represents the inputs in the alphabet, symbols call the input alphabet, and O represents the output alphabet, and gamma represents the transition functions, and X represents the transition functions with respect to output, gamma with respect to input, and X with respect to output, and Q naught is the initial state where the input is proceeded like Q subset of, or else Q is a subset of Q, right? So this is how I can represent the Moore machines. And if you observe that how a state diagram or else how a state table can be written with respect to Moore machines. So the Moore machines consist of present state, next state and the output. If you observe the Mealy machine has present state and the next state. The next state will be observed only with respect to the present state input. That means what, the output depends upon the present state as well. Whereas the Moore machines, the output output depends upon only on the present state but not the past history inputs, right? So the state table of Moore machine is the present state, next state and the output. So the next state goes with when input 0 and when input 1. Okay, so here we have 4 states, A and B and C and D. And here in the Moore, how can we represent is, see, this is with respect to x2, A x2, right? So this is the output, A x2. How we got the output is, the output depends upon the next state as well. So when the transition is taking place from A to B, so when the transition is taking place from A to B, we are saying that when input is 0, say from A to B when input is 0. So this is the input. When input is 0, we are getting the output as x2. When the input is 1, okay, when the input is 1, see here it is a 1. When the input is 1, the transition is going towards C. Right? When input is 0, the transition is going towards B. When input is 1, the transition is going towards C. So that is what we are representing here, B and C. And in all such cases, the output is formed as x2. Okay. And then, for example, so this is my present state and this is my next state. And if you are considering your present state as B, so this one, if you are considering your present state as B, remember that the output you obtain from the present state inputs and the past output as x1. Okay, B/x1, that is the output. So how we got this x1 as output is when the transition taking place from B to C. So from when the transition is taking place from B to B itself. Okay, B to B itself, we are saying that the output is observed as 0. When the input is 0, right? When the input is 0, my output is x1. And when my input is 1, when the input is 1, what happens is, here the transition taking place from B to D. The transition is taking place from B to D. So that's the reason when the input is 1, the transition is taking place from B to D, right? So that is how we will be writing our, that's how we will be drawing our state diagram. Okay, state diagram is purely depends upon the state table. Okay, this is a state table. And then if you're considering the C as well. So the C is when the input is 0. Okay, when the input is 0, what happens? It is taking its transition to D. Right? When the input is 0, it is taking its transition to D, where my output is x2. When input is 1, it is taking its transition to D as well. Okay, itself as well. So it is 0. When if it is 0, it is taking its D. When if it is 1, it is taking its transitions towards a D state. Okay, and then finally with the last state, that is a D. So here, this is how the transition goes with respect to the inputs, when the input is 0 and when the input is 1. Okay, so remember that the Moore and Mealy machines, these two are the basic finite state machines, where the output in the Mealy machines, the output depends on the present state and as well as the past input, whereas in the Moore machines, the output depends only on the present state of the inputs. Okay, and then Moore to Mealy. And now we will see how the Moore to Mealy the transition goes on. So here there are a few steps to follow if you want to transmit, or else if you want to transit from one state to another state. So here the input is Moore machine. So what are we doing now? We are just transition is taking place from Moore to Mealy. So in this case, our example, the input must be Moore machines. So the Moore machines, output must be Mealy machines. So from Moore to Mealy. Okay. So my step 1 is take a blank Mealy machine, Mealy transition table format. So first and foremost thing is, you just consider a Mealy machine. Okay, the transition has been taken from Moore to Mealy. So consider the Mealy transition table format. And then second one is copy all Moore transition tables into this table format. So first consider the Mealy table, And then second one is you just copy all the Moore tables, okay, all the Moore mission transitions. So there is a lot of difference between melee transition table and Moore transition table. But in order to transit the in order to transit from Moore to melee, the thing you have to do it, just copy all the Moore transitions towards the melee transition table format, and then check the present state and then corresponding outputs to the Moore mission state table. So now what we have to do is, after copying the Moore emissions, we need to check, or also we need to check the corresponding outputs with respect to the inputs, right? Then if for a state Qi output is M, see, for a state Qi output is M, for a state Qi output is M, copy it into the output column of melee mission. So if for suppose we are getting the output as M, and then we have to copy all this output to melee missions table, okay, right? So melee missions table with whenever Qi appears in the next state. So whenever in the next state, if you are appearing as Qi, then what you have to do is copy this output which is come from with respect to the Moore emission, copy it and dump it to the melee mission. So and then say this is an example they have given. Convert the following Moore missions into its equivalent melee mission. So how can we convert? Is, see, here we have Q1 and Q0. Q0 and Q1 are the two states with respect to the output. So these are the outputs. See, this sort of transition state we have seen in Moore, right? Moore. So now we are converting this Moore to melee. So when output is 0, what happens is the transition goes with respect to input as A. Okay, when if it is B, it is taking its transition to Qi. So here this is what the transition Moore table. So Q present next state. This is the next state. This is a present state, and this is the output. Okay, when Q0 is a present state with respect to A, when the input when the next state, that is when input A as A, what happens is it's staying in the same states itself, okay, Q0. But when your input as B, what happens is we see the transition from Q0 to Q1, okay, when from Q0 to Q1. Likewise, when with respect to Q0, so Q0 is see, with respect to Q1, Q1 is, it will be within itself in the same state when the input is B. But when the input is A, what happens is we see the transition from Q1 to Q0, okay, and then the output goes with respect to 0 and 1. And now coming to the state equivalent melee mission can be obtained as follows. So here melee, we are converting the Moore to melee, right? So now we will obtain the melee equivalent missions. The observations are like this. With respect to Q0, okay, delta Q0 A and delta Q0 B. So with respect to delta Q0 A is 0 and Q0 B is 1. Okay, Q0 A is 0, Q0 A is 0 and Q0 B is 1. Okay, this is with respect to melee missions. And now we will see with respect to Q1. Q1 A means 0, Q1 B as 1. So previously what did we observe? Q0 A as 0, Q0 B as 1. Okay, these are our observations out of the when we convert the Moore to melee. This is what we have observed. We have observed is Q1 and Q0. Q0 as 0 and 1 and Q0 as 0 and 1. This is what we have observed when we have converted the thing from Moore to melee. And this is how we can draw the transition table. So the transition table for melee can be drawn as, see, these are the states, right? Q0 and Q1 are the states. And my input as 0 and with respect to input as 1. Okay, with respect to input 0 and input 1. With respect to input 0, what I was saying that Q0 is it is within itself, that is Q0, and the output as 0. Okay, when if Q1 as Q0 as 1, okay, as Q0 as 1, what happens is the output will becomes 1. Then with respect to Q1 as B. Okay, when Q1 as 0, we are saying that the output, it will be within itself the state as Q0. And if it is 0, if it is within itself, then the output as 0. And if it is taking its transition from Q0 to Q1, then the output goes as high, that is 1. Okay, so this is a simple basic conversions of how to convert a melee to mode. And now we will see the lambda for state Q1 is as follows. So here we know that there are two states, Q1 and Q2, Q1 and Q0. So now we will see the state for lambda. Okay, lambda for both the state, how it varies. So we know that Q1, lambda Q1 as 0 and lambda Q1 B as 1. Okay, so for A as 0, B as 1. So these are the states just now we have discussed, and from the state transition table, we can draw the state diagram. Okay, so the state diagram, this diagram is in terms of melee. Okay, in the mode type, we will be writing like this. This is the output and this is the state. Okay, so the length of the output sequence, is n plus 1. In the Moore machine, the length of the sequence is n plus 1, whereas in melee machine, the length of the sequence is n. Okay, so these are the two states, Q0 and Q1. And the output, if it is with respect to the output, the state goes as it is 0, the state will be in itself, and if it is taking its transition from Q0 to Q1, then it is like B, and the output goes as 1. Okay, similarly happens with the same state Q1. Okay, if it is taking its transition from Q1 to Q0, then remember the output is 1. Okay, when the input is A, output is 1, and when you are observing the output as 0, it means that the transition is taking place from Q1 to Q0. Okay, and then see, this is the ultimate solution for the transition that is taking place from Moore to melee. So in the exam point of view, if I have come across that how to convert or the transition, that how to transit the states from Moore to melee, the best thing is you just write down what is Moore machine, what is a melee machine. Okay, and then you consider, there are the 3 steps to follow. First step, second step, and third step. First step is, if you are converting that Moore to melee, write down draw the transition table of melee, and then second one is copy the things that is having. First you have to draw the table. Okay, first one is draw melee table, then copy the content of Moore and drop in the melee table. Okay, drop in the melee table, and then finally go for the regular calculations, proper calculations. Okay, so this step 1 and step 2 are the major things, or else they are the main important things if you are going for the conversions. Okay, the transitions. So remember that all these things will be very important, and also the important steps to follow is step 1 and step 2. Okay, once you are done with step 1 and step 2, then it is easy for you to convert these two, and the step 3 is very easier to follow if you are done with the step 1 and step 2 as well. So this is one of the basic thing, or else it's one of the easiest way to solve the problems if you are come across to convert from melee to Moore and from Moore to melee. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.